We are on to 2.7. Very, very exciting. We finally get to discuss the derivative here, a huge part of our course. We call this the derivatives intro because we're going to spend a couple of sections really unraveling just techniques to find the derivative. So here's where we begin. We want to know the instantaneous rate of change of f of x at a. So if you watch the What is Calculus, that video, you saw a graph sort of like this. So imagine some function f of x, right? Could be anything, and a location a. The instantaneous rate of change of that function at a can be visually seen by drawing what we call the tangent line. So the tangent line, it kind of comes up, it just barely grazes by the function. It passes through just one point and then continues on its way. So sometimes you hear people say it moves in the same direction as the function does, just grazing by. How does this tangent line help us to know the instantaneous rate of change? So we're really thinking, how fast is f of x increasing right at that moment? Okay, so the tangent line will it's going up, right? Really, the important attribute of that tangent line, and this comes up in the first project, what is it about that tangent line that is describing how fast f of x is changing right there? And it's the slope. So really what we're looking at, or what we want to know, is the slope of that tangent line. So we could certainly calculate the equation of the line, but really the big attribute, what's really important to us, is the slope of that line. Okay, so how can we even begin to start to figure out the slope of such a tangent line for a function at any given location? So we're going to think back, actually go back beyond, before pre-calc, way back to algebra, where we first learned about slope. Okay, so here's another drawing. So typically when we think about slope, we think about connecting 2 points on the xy plane. So what I've drawn 2 points. I tried to draw that same function again, and then I identified 2 points on the curve. One of them is at A, and then one further back this way I just called X. So there's a reason I give them these names for the formula that's going to come out of this. Okay, but then, so the line connecting the 2 points, we refer to it as a secant line, and like secant tangent. So it probably reminds you of the trig functions. Turns out it's just the same name. There's no connection to the trig functions here. It just happens to be the same words. Secant line, if that's not clear. So I've got my tangent line there, big and bold. How is the secant line helpful to figuring out the tangent line, or the slopes of these lines, is really what we want. So here's the idea. If I draw another point back over here and I connect it with A, we're thinking, is this line a very decent approximation for this tangent line? Like, well, no, not at all. They're nowhere even close. But what if I did something? What if I moved the x a little bit closer? Maybe halfway. And I made the point right here. And then I drew another secant line connecting that new point with A. Like this. I'll extend it back this way, and we'll extend it up. So there's my second secant line. Is this secant line a better approximation to the tangent line? I would say so. What if I moved it even closer? What if I put that x maybe even closer to a, and I thought of this point on the function? And it's starting to get, kind of messy, but okay, I'll connect this point with a, and I'll get this line right here. And we can see, wow, each time I move x closer, that secant line is looking more and more like that bold tangent line. What if I was to go even closer and closer and closer? Okay, I won't draw any more, but we get the idea. Here's the thing. As x approaches a, the secant line approaches the tangent line. As x approaches a, the secant line, kind of running out of room, the secant line approaches the tangent line. There's a limit going on. All right. Let's back up a second. We want to get a formula for this. We can see the concept. As x approaches a, my secant line is approaching my tangent line. Very cool. Okay, let's push pause on that, and we'll come back to that idea of a limit. So I'm calling this the average rate of change. You see that at the top. I never mentioned that. Whenever you think about the slope between 2 points, the slope of the secant line we call the average rate of change of the function, where just the slope of the tangent line at one point is at a given instant. It's not the average between 2. All right, so where's this headed? I'm going to kind of slide my paper over this way. I'm actually want to not reveal what's over here just yet. Sorry for this sunlight kind of poking through. It's a bit breezy here. All right, what do I have on the side here? This is the formula for slope. Again, way back, when we first started algebra, we learned this sort of thing. y2 minus y1 over x2 minus x1. Think about the 2 points on the secant line. We had x and we had a, right? Maybe even that first secant line. Well, we've got the difference of the y values of those points divided by the difference of the x values. For us, if our points are x and a, we could say the difference of the y values is f of x minus f of a, right? The y values of the 2 locations. Divided by the difference in the x values, well, those were x and a. So difference of the y's, difference of the x's, f of x minus f of a over x minus a is the slope of the secant line. And that's the same slope that we're used to calculating. Now we said, hey, if you want to use the secant line to figure out the tangent line, take the limit as x approaches a. So if I want the slope of the tangent line, all I got to do is take the same formula for the slope of the secant line and throw a limit in the front. And that's what I've got right over here. The slope of the tangent line at A is m equals same formula, f of x minus f of a over x minus a, but I'll put this limit here in the front, the limit as x approaches a. And we can get it. Pretty cool. Okay. A little bit more theory, and then we'll be ready for some examples. I'm going to try and keep that there, that formula right there on the screen. We're going to talk a little bit about just some of the language that we're going to encounter and some notation. Whenever you learn a new concept in math, it always comes with new notation. And sometimes the notation is just as difficult to wrap your head around as the concept. So what do we have here? Okay, so we're going to refer to the slope of the tangent line. We're just going to give it the name derivative. Okay, so people realize this was such a big idea. We don't want to have to keep saying the word slope of the tangent line. We want one word to capture that. And so somebody chose the word derivative and it stuck. All right. Also, there's a way of writing it. So we don't say m. It is a slope of a line, but we're not gonna use that. We're gonna use this notation here. So this is kind of bizarre. If you've never seen it before. So that's that. It looks like f of a, but then there's this little mark there up above, and it's just kind of a little tick mark, like an apostrophe, or it's called a prime. So you would read this as f prime of a. And it means the slope of the tangent line for that function at a. Or you might say the derivative at a. But this thing is equal to the same formula we just discovered. It's just a new notation, and we've got this new word derivative to replace the phrase slope of the tangent line. Okay. Lastly, before we move on, we've been using different phrases this whole time, sort of interchangeably. When we say the word derivative, so just said it a bunch, the slope of the tangent line is what that means graphically. It's the same thing as the instantaneous rate of change. How fast is the function changing at that moment? Or you might hear, what's pretty common is to hear the instantaneous velocity, right? Change, velocity. How fast is the function changing? What's the velocity? Especially if you're talking about, we get some physics examples, and in your project, right, you've got an example of a watermelon falling, right? It has a velocity. We would refer to its change as its velocity. Okay, so whenever you hear, the point is, whenever you hear, one of these phrases, just know that they mean the derivative. They all mean the same thing. They're interchangeable. Okay, I think we are going to stop this video here before we get to the first example. We'll do that in the next one.